Welcome to the third video in this introduction to R series. In this video we will be taking on data structures and variable types, how to create them, how to navigate them, and how to manipulate them. So learning how to use R unavoidably requires you to familiarize yourself with the types of data structures that R has to offer. The most used data structures are vectors, matrices, data frames, and lists. Learning R also probably means that you must think differently about data than how you are used to. From software such as SPSS or Stata, you are probably used to working with a single data structure, which is your dataset. So what you're used to thinking about as your dataset is often stored in a data structure named DataFrame in R. However, in R, your variables do not have to be part of a data frame. Here, we will introduce the different kinds of data structures that there are in R and how to navigate and manipulate them. The first data structure that we will account for is the vector. Now, vectors are the most basic form of data structure, and you can consider matrices and data frames, which you will get to later, as individual one-dimensional vectors that are assembled into two-dimensional tables. So, contrary to matrices and data frames, which are two-dimensional, that is, they have rows and they have columns, vectors are always one-dimensional, meaning that they just stretch out in one direction. So, people often like to think of a vector as representing what you're used to thinking about as a variable in a dataset. That is, it is common to visualize the vector as a column in a spreadsheet. However, a vector does not have an actual spatial orientation. That is, a vector in a dataset can represent one person's responses to several variables. That is, it can represent a row, or it could represent several people's responses to one variable, making it to represent a column. It can also represent a single person's response to a single variable, meaning that the vector consists of a single value. Outside of a dataset, vectors do not have to represent variables or individuals. Vectors can be used to store any sort of value in R, where what constitutes a value does not have to be a number. The requirement is that the elements of the vector is of the same type. That is, you cannot store a number and a word in the same vector. If, for example, you were to try to store the value 1 and the word 1 in the same vector, if you try this, then R will store the number 1 as a word, which you see here in the output, that the 1 is encapsulated by quotes, meaning that R has stored it as a word and not as a number. There are several types of vectors that store different kinds of information. The most common of these are the numeric vectors, the factor vectors, the character vectors, and the logical type vectors. You could include the integer type vector among these. However, for present purposes, it's sufficient to think of integer vectors as just numeric vectors. That is, the difference between an integer vector and a numeric vector is that an integer vector stores numbers such as 1, 2, 3, 4, 5, etc. That is whole numbers, while numeric vectors can store numbers using decimal places or including decimal places such as 1.1, 1.2, 2.4, 3.14, etc. However, with respect to what kind of mathematical or arithmetic operations you can perform with them, there is no difference. Both you can use the mean function, for example, on both an integer type and a numeric type vector. So you can ask R what type a vector is by feeding the vector object to the class function. Now here I have pre-made some vectors before starting this recording here, and we can check out the contents of these vectors. Let's see here. If I print out age, we see that the age vector contains whole numbers, that is integers. We see that the degree vector contains some values. You have PhD, master, PhD, bachelor, etc. So this contains, or is supposed to contain, the degrees of individuals. You have the gender variable, which we see here contains the values male and female, where the values are enclosed in quotes, meaning that these are words. And finally, you have the married vector, which includes logical values, false and true. Now we can check, for safety's sake, what kind of objects these are, what classes these vectors are, by wrapping the class function around the object. And we see that the class of age is numeric, the class of degree is factor, the class of gender is character, and the class of married is logical. So we now move on to considering different vector types. The numeric types of vectors are probably the ones that we are most used to working with. So these store numbers, and since they store numbers, they are vectors that you can do arithmetic operations on. So factor vectors, on the other hand, store information that is nominal or ordinal. So these are sometimes more complicated to work with than the numeric and integer vectors. However, it can sometimes be useful to store information as factor vectors. So there are some circumstances where it's quite convenient to store categories or category memberships in a factor vector. That is, if you take the lm function as an example, which fits the linear models. If you feed this linear model function a factor vector, the lm function will automatically treat the vector as a set of dummy variables. On the other hand, some operations cannot be performed on factor variables that you might otherwise want to do. You can, for example, not take the mean of a factor vector. It will return an error. So, for this reason, sometimes it is convenient to store categorical and ordered categorical values in factor variables, such as in the case of the lm function, and other times it is inconvenient, such as in the case in the mean function. So character vectors contain words or strings of words as elements. So often this is a preliminary state of data before they have been coded in a way that allows for statistical analysis. So, for example, a vector could contain text scraped from social media, which could then in turn be submitted to natural language processing, which actually includes functionality for doing. The final state that would be then where these codes are fully categorized and coded so that they can be analyzed statistically. And there are other uses for character vectors as well. They are quite often used in R for model specification in different user-written packages, where one notable example being the Lavan package for doing structural equation modeling. Logical vectors can take on only two values, true and false. So a vector of logical values can be submitted to some arithmetic operations. Since R treats the value true as 1 and the value false as 0. As such, you can take the mean of the married vector that we made previously, and it returns the value of 0.3, which is to say that the state married is true for 30% of the individuals in this dataset. That is, 30% of the individuals are true or are married, and 70% are then not. So logical vectors have several uses, specifically in programming, or particularly in programming, as I stated previously in the last video. However, for most people's uses, they are probably the most useful for subsetting data. So when it comes to assembling or making vectors, the following is the simplest and perhaps the most important function you can learn in R, is the C function. Now this innocuous little fella allows you to combine values, that is, to assemble them into a vector. So the type of information you feed the C function determines the class of vector that is created. So for example, the C1, 2, 3, 4, 5 will then create a numeric vector. You can store this as my numeric. If we take the class of this, my numeric, we see that it is a numeric vector. If you make a new vector called my character and say 1, 2, 3.14, etc., we create a vector called my character, which includes these words here, or these strings of words. So we have the class of my character. We see that it's a character vector. In other words, the type of information that you feed the C function determines what kind of vector it creates. And you can do this for logical values as well. You can make a vector called my logical, which we can feed the values true, false, false, true, false, just as an example, not in quotes. And if we print this and check its class, we see that it is a logical vector. So chances are that this C function here is something that you're going to be using a lot. So it is something that you should make note of. Making a factor vector is a bit more complicated than making the character, logical, and numeric vectors. So to make a factor vector, you have to use the dedicated function factor. And it takes as input first the values. There's this x argument here. And these values you assemble using the C function. So if I say, for example, male, female, 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 and do this, it creates a factor variable with the values male, female, 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 and the levels female and male. Now, a factor variable can consist of more levels than what is actually observed in your data. So if we go on to specify as levels in this factor variable, if we supply it with some additional strings here, male, female, and other, for example, then it makes the factor variable. However, this time you see that the levels include other, meaning that the factor variables has room for people who are then categorized as other, that is not as male or female. So it's possible to force the factor variables to have an ordering for these values. In the current case, it doesn't make sense. However, for the degree variable that we have above here, the degree vector, we see that I have ranked these degrees where bachelor is less than master, which is less than PhD. So in order to do this, we could, for this variable as well, even though it doesn't make sense, is to specify the additional argument ordered equals true. In which case it would produce a factor vector that would say that male is less than female, which is less than other, etc. So in order to, for all of these functions, obviously you would find great help in using the help file. So in the case of the factor variable, we could check out the help file for the factor function, which would provide you with additional arguments that you could specify in order to make a factor variable. However, we won't be going through this at this point in time. So I haven't explained, but I have already demonstrated how to navigate vectors, which is to enter a vector and to extract specific values from it. So accessing a specific value or values in a vector is done using these squared brackets like this, which then follow the name of the vector object which you want to navigate. So if you take the age vector, for example, and we want to retrieve the fourth value from age, which in this case turns out to be 38, we can inspect the entire age vector like this. We see that I ask for the fourth vector in age, and I get the 1, 2, 3, 4th out, which is 38. So you can ask for several. I can ask for the, for example, the first and the 10th value of the vector like this. I get 39 and 39, and inspecting the age vector again, we see that the first value is 39 and the last value is 39. So here you see already a very common use of the C function that I pointed out above. So this subsetting here can also be used to change the values inside a vector. So if I want to change any single value or any number of values inside of the age vector, let's just take the first one for now into another value. I can say, as I showed in the previous video, I want to replace the first value in age with the value NA. If I now are to open this and we inspect it again, we see that by subsetting or showing R2 the first value of the age vector and assigning the value NA that is missing to this first value, I took then this first value and changed it into NA. So using logical vectors, subsetting can also be used to change several values at once that satisfy specific criteria. So for example, if I use the following code, gender, for which gender is equal to male, and I want to change all of the values male in the gender vector with another value, say for example not female. We can let me display this first, and I do this. And if I now check the gender vector again, we see that all of the values for male have been changed with or into not female. And so I can only obviously do the reverse operation here and say gender for which, or I can actually say for gender for which is not equal to female. I can say male and run this code and check the gender vector again, and we see that all of these values that were changed to not female have now been changed back into male. So you navigate vectors then by using these square brackets. And you can use this navigation to manipulate the contents of a vector by following up the brackets with an assignment operator such as this, and then the value that is to replace the values that you have specified within these square brackets. So let's move on to the data structure called the matrix, or in plural, matrices. So matrices are vectors that are stitched together as rows or columns. So in order to combine vectors into a matrix, you can use the matrix function. So a matrix can be considered a two-dimensional vector. Let's just, for the sake of it, quickly assemble a matrix here. See here that by adding the age variable twice to a matrix and saying that I should have two columns here, I have produced a matrix considering of the first age variable as the first column and the second age vector as the second column. And these rows here then represent individual cases. So, as is the case with vectors, matrices can only store one type of value. So that is to say that a matrix can contain, for example, both numbers and words at the same time. If I were to try this, as in the case with vectors, and I add the gender variable instead of the age variable twice, you see here that I produce a new matrix here with the first column being the age vector and the second column being the gender vector. However, you see here now that the values inside of the age vector are then enclosed in parentheses, or sorry, in quotes, meaning that they are now transformed into a character vector, meaning that they are not considered numbers anymore by R. So this is the same type of conversion that R did previously for the vector that we tried to make that contained both the value 1 and the word 1. So as for assembling matrices, I've already showed you how to do this here, but I'll go through it in more detail. So the matrix function allows you to supply the values that the matrix is to hold as the first argument. So if we pull up the help file for the matrix function here, we see that the first argument for the matrix function is the data. So this data you enter using the C function. So matrix data equals C, and in here you specify the data. However, since this is the first argument, we do not have to specify the name of the argument. So these values can also then be vectors of values. So as I did above here, I specified the age vector, not a single value, but the age vector as the first object to combine using the C function. And then the age vector again, seen as how these this is the only numeric vector that I have available at the moment. Furthermore, as we can see, the matrix, the next two arguments of the matrix are the nRow and the nCol functions, where you really need to specify this. If we do not specify either the number of rows or the number of columns in the matrix and just run this, the matrix will just have a single column that stacks the two objects on top of each other. So for this reason, you should always specify either the number of rows or the number of columns the matrix is to consist by. Personally, I find it more intuitive to specify the number of columns because basically you know how many variables, so to speak, the matrix is to consist of. In this case, we supply the age vector twice here, so we have two objects that are to be combined into a matrix. And I'm saying that this matrix is to consist of two columns. And if I do this, it produces this matrix here. So, as is the case for vectors, you navigate matrices using the square brackets. So first, let's just save this as my matrix using the assignment operator once again. So I can navigate this my matrix using these square brackets. However, at this time there are two dimensions and in the vector, and these dimensions are separated using this comma operator here. So to the left-hand side of this comma, I specify the rows, and to the right-hand side of this comma, I specify the columns. So in this case, if I want the value contained in the first row and the first column, I specify my matrix square brackets 1, 1, and I get the NA value, which is this value. Similarly, I can move on and say I want the second value in the first column, and I get the value 34, which is this one. I can specify several values at once. I can say I want the first and second value of the first and second columns, like this, and it returns me with the first two columns and the first two rows of this matrix. Now it doesn't have to be in order like this. I can say I want the first and the third. First and the third rows. And it returns to me the values NA, which is the first column, and the values 37, which are located on the third row. So then this code here then asks R to retrieve the values that are found in the intersection between rows 1 and 3 and columns 1 and 2 of the matrix. Now, also as with vectors, you can manipulate or change matrices by following up the brackets with the assignment operator. So as in the case above, if I want to replace the values in this intersection here between rows 1 and 3 and columns 1 and 2 with some other values, say for example 100, I would just write this code here where I asked R to retrieve these values, and by doing this, by choosing these values again and using the assignment operator and typing out what I want to have assigned to these rows and columns, and run this, run my matrix again, or call my matrix again, you can see here that I changed the values of the first row and the two first columns, which are the only columns in this case, and the third row with the value 100. So another way of navigating matrices is to use the names of the rows and columns instead of the numbers of the rows and columns. You see here in this case the matrix only contains numbered columns and numbered rows. However, we can change this using the row names functions for changing the names of the rows, and the col names functions for changing the names of the columns. Now, in order to do this, we can input the my matrix here as the first argument of the col names function. We can assign to this the values, let's say age1 and age2. And if we then call this matrix again now, you see that these two columns here now have names. Now we can do this for the rows as well. Let's say row names my matrix, and we can assign, let's say, person 1, person 2, and we just do this down to the 10th person, 3, 4, 5, 6, 7, 8, 9, and 10. Run this and then call the my matrix again. You see that we have changed the names of the rows from just numbers 1 through 10 to person 1 through person 10, and the new names of the columns are still h1 and h2. So instead of writing this up here that we did previously to navigate the vector using only the numbers, we can now enter these same values by their names, the names of the rows and the vectors. So I can supply here give me the person 1 row and the person 3 row for the age1 vector and the age2 vector, and it returns these values then, these that we changed to 100 previously. And we can also then use the same navigation and selection to assign new values. So let's change these to a random number, let's just say 1, 2, 3, 4, and calling this matrix again now. You see that I did the same type of alteration to the matrix as I did using navigating them using the numbers, here now using the names of the rows and the columns. So another efficient way of manipulating matrices is to use logical subsetting. So here I imputed the value 1, 2, 3, 4 in some selected entries of the matrix. So I can choose to select these in bulk quite simply by writing my matrix, for which my matrix equals 1, 2, 3, 4, and I get these 4 values out. Now if I want to say that this value 1, 2, 3, 4 is how some values are marked as missing in other software, for example M+ asks you to assign some numbers that are to represent missingness. Now assume that you got this data here from M+, and it was intended for use in M+, and you want to make it ready for use in R. You can change then these values 1, 2, 3, 4 to NA in one go without having to specify exactly where they are located, like this. So here I specified that R should select these values, all values in a matrix that are equal to 1, 2, 3, 4. And if I want to change these to the R way of marking missing values, I can write NA here, press enter, and if we then inspect the matrix again, see that all the values that used them to be 1, 2, 3, 4 have been changed to missing. So that does it for matrices. How to assemble them, navigate them, and manipulate them. And let's move on to data frames. So data frames, like matrices, are two-dimensional. They organize data in rows and columns, where the rows represent cases and where columns represent variables. So, unlike matrices, data frames allow you to store different types of vectors as distinct columns. Recall that in a matrix, all of the columns or all values have to be of the same type. You can't store values or numbers and characters, for example, in the same matrix. However, you can do this in data frames. So, unlike matrices, data frames can include numeric, character, factor, and logical vectors at the same time, represented in distinct columns. So, as for assembling data frames, you can assemble data frames using this data.frame function. This function takes vectors as arguments and assembles them as columns in the order that they are supplied. So if we want to include all of these vectors that I made beforehand here, the age vector, the degree vector, the gender vector, and the married vector, we can assemble these in a data frame as such. I say age equals the age function. So here I am assigning a name to the column that is to represent the variable age. We have the degree vector, where we assign the degree object that is located in our environment. We have the gender variable, assigning the gender object that is in my environment, and the married vector, which is to represent the married, or is to consist of the married vector. So we see here that all of these vectors that are of different types have now been assembled in one and the same data frame. Now I can make a data frame, then store it as a data frame as such. And we can find it here in our environment. So that is how simple it is to assemble a data frame in R. Now, as for navigating and manipulating data frames, for the most part, this is identical to how you would do it for matrices. There is, however, one additional way by which you can navigate a data frame, and that is by this $sign operator. So you can select one column of the data frame by following the data frame object up with the $sign operator. So I can do my data frame, follow up with the $sign, and you see here that I get a selection of the different vectors or the variables contained in the data frame. So if I choose this age vector here, press Ctrl Enter on my Windows computer, you see here that I get the age vector. It prints out the age vector. And now I can choose specific values within this vector as I would otherwise. Let's see. Let's take the 4th and the 6th value. And it prints out the 4th value here, which is 38, and the 6th value here, which is 37. So one drawback of selecting variables in this way is that we can't select several variables at the same time, and this is something that we can do if we use the brackets. So if I want to choose the 1st and the 3rd column in the data frame at once, I would do this comma. And again, this at the right hand side of the comma you can select the columns, and at the left hand side of the comma you can select the rows. So not selecting any rows, so to speak, tells R to select all the rows. So I can choose the age vector, for example, and I can choose the gender vector, for example, and it prints out these 2 variables. I can also supply the location using numbers of these variables, 1 and 3, and I get the same thing. Now, manipulating these data frames is then done the same way as you would a matrix. So if I want to change this NA value on the age vector, which is located under my data frame age, and it's the first one, if I want to change this to, for example, the value 40, that is 40 years of age, I can do this. And inspecting then my data frame age, again you see that I changed the first value of the age vector located in the my data frame object to 40. And we can see if I print out the entire data frame again that I did this, and I can change, just as with the matrix, I can change several values at once using 1 and 2 using this subsetting here. So doing this, I changed the first 2 values of the age vector to missing values. Now the final type of data structure that we will go through is the list. Now lists are very useful because they, just as data frames, can store any data type. Unlike data frames, however, they do not require that the objects they contain are of the same dimensions. So when visualizing what a list looks like, it might be useful to draw on the metaphor of the folder. So a folder on your computer can hold any type of file and even other folders. So this is also how lists function. You can store anything you make in an R into a list, even other lists. So one and the same list can contain all types of vectors, matrices, data frames, and any other class of objects, such as, for example, a regression model. So this feature of a list makes them extremely convenient to use for storing objects in R. So lists can be assembled using the list function. So as for with data frames, the objects are supplied to the list sequentially in the order that they are to be stored. So to make a list containing the age, gender, and degree and the married vectors here, you would do it like this. So provide the age, the gender, the degree, and the married objects that are contained in my global environment. And you will see that it's stored like this, or the printout of the list that it makes looks like this. So you have these double parentheses followed by these single parentheses here. So we will go through what these double and single brackets mean. So once you have created the list, you can add further elements to it using the assignment and the $sign operator. Or you can use these square brackets. So imagine that you stored the list above as my list. So let's do this. Now I stored this in my global environment here. You can add the mean of the age vector to this list. As such, let's just make sure that the age vector does not contain NA. It does. So let's impute age 1. Let's just place 40 in it. So we can store the mean of the age vector into my list using the $sign operator like this, and say call this age mean, and we can use the mean function on the age vector. And if we then open the list again, we see that we have added the age mean object to the list. So while lists are extremely simple and convenient for storing objects, they can be quite complicated to navigate. So navigating lists with brackets requires the use of these double square brackets like this. This is because if you use single brackets, you are extracting the list element itself rather than the list contents. So this can again be more easily understandable if we draw on the folder metaphor. So using these single brackets here is then equivalent to selecting a folder, while using these double brackets here is equivalent to entering the folder and retrieving the contents of the folder. So the $sign operator functions the same way as using the double brackets, in the sense that it extracts the contents of the list element rather than the list element itself. However, using the $sign operator requires that the list element is named, which is not always the case. So, for example, the code that we use to assemble the mylist object above does not name the first 4 elements. So you see here that you have a numbering of the list elements here rather than a name. And here for the age mean, you can see that we actually gave it a name this way here. Now we could have assigned names to the object of the list by doing this operation here. So in this case, I recreate the mylist list and I name the age vector. If we open this again, let's see what it did. So now you see here that I have this $age, which allows me to enter the age list object using the $sign operator. So the age mean element that we made was then named when we stored it, and we can as such access it using the $sign operator like this. So manipulating lists follows the convention that we previously described. So first, new elements can always be added to the list by assignment. So for example, that what we did previously, I can add to the my list a new element that we can call prop married, so the proportion married, by taking the mean of the logical vector married. Open this then, prop married. I added the proportion married. Also, I can say, so this is then stored. Let's open it again, my list. Prop married is then the 6th element of this list. We can count it 1, 2, 3, 4, 5, 6. So if I want to edit this, I open it. Using this double square bracket, I enter the prop married object, and I can, again, let's just say that I'm imputing an NA here, and if we open my list again, I have changed the contents of the prop married object with a missing value. So an object can then also be altered within a list. So let's say that I want to alter this 4th element in the age object that is stored in the list. I can go into the list and I can choose, as I would otherwise, this 4th element in the list, which is this 38 here. And I can change this to another value, 1, 2, 3, 4. And if we open the list again, we see that I changed the 4th value of the age object to 1, 2, 3, 4. Now I can use the numbering as well. So the first element in the first stored object in the list and the 4th element in this first list element. I can change this to NA, for example. And now opening my list again, we see that I changed this 4th value down to NA. So what I'm telling R, basically using this line of code, is take the first element within the myList object, move to the 4th element stored within this first element of the myList object, and impute the value NA. So that does it for this video. We have been accounting for the different data structures and variable types in R. We've gone through how to create them, how to navigate them, and how to manipulate them. We took 4 types of data structures and went through them. We went through the vectors, we went through the matrices, we went through data frames, and we went through lists. So this is not an exhaustive account of the data structures that exist in R, but it is a good starting point and probably the most common types of data structures that you are going to be dealing with when working with R.